This video is over conservation of energy. When you hear energy is conserved, that holds for all forces. Now, we're going to focus right now on the conservation of mechanical energy, which only holds for conservative forces. So, I'm going to explain a little bit about conservative forces right now. Conservative forces are things like gravity and springs. So, this section only has to deal with both of those things. And springs. Now, things that are not conservative forces are things like friction or drag, but we're going to focus that a little bit more when we start talking about work. So our mantra for this section is energy cannot be created or destroyed. It can change forms and it can transfer from one object to another, but it is not created nor destroyed. So we're going to focus on conservative forces again, and so the energy that we're specifically talking about is mechanical energy. In our last video, we talked about spring potential energy, gravitational potential energy, and kinetic energy. All of these three things are forms of mechanical energy. Now, if there are no non-conservative forces like friction or drag, then our mechanical energy at the beginning is equal to our mechanical energy at the end. So our equation for mechanical energy was any spring potential energy, any gravitational potential energy, and any kinetic energy we have at the beginning should all equal the same amount of mechanical energy at the end. So if we have any spring potential, any gravitational potential, or any kinetic energy at the end, these two values should be the same. So when it comes to creating the equation that you're going to eventually end up using, you really want to choose from this selection up here. So on the left are any types of energies you have at the beginning of your situation, and on the right is any type of energy you'll have left at the end of your situation. And so we're going to look at a couple of examples to help you kind of build this strategy. So this is a very typical problem that we saw last year. For example, a 5 kilogram mass initially at a height of 2 meters drops to the ground and ends up with a speed of v. Ignore air resistance. Again, air resistance would be a non-conservative force, so mechanical energy would not have been conserved. So again, if you look at our equation, which right now is just that giant piece, we don't have a spring involved, so actually these two pieces will go away. Now, at the beginning of our situation, we have no velocity, so this piece also goes away. At the end, when we finally reach the ground, we have no height. So, all we have left is our potential energy at the beginning should be equal to the kinetic energy we have at the end. So I'm going to go through about 5 examples that cover different situations that you're going to come across. And this is going to help you build the equation you're going to need to use. So for this section, you don't need to write everything down. It's really just doing the equations with practice. So here we have a roller coaster starts at rest at the top of a 20-meter tall hill. Determine the speed of the roller coaster when it reaches halfway down the hill. So this is where we begin, and here in the middle is where we want to determine our energies. So at the beginning, we only have potential energy. At that middle point, we're going to have both height and speed. So our equation will look like this bottom part. mgh naught, again, our initial height, is equal to mgh, our height at that point, plus 1/2 mv squared, our velocity at that point. In this example, we're looking at the same roller coaster, but now we want to know what the speed is at the bottom of that 20-meter tall hill. Now, you could use the energy that you solve for here in the center, but really, it's a lot easier if we just go back to the beginning. So, at the beginning, we had gravitational potential energy, mgh. And then at the end, we're only going to have kinetic energy. So we'll have 1/2 mv squared down here at the bottom of our hill. So our equation will look like this. So this problem might look a little bit familiar. It says the projectile is launched with a speed of 30 meters per second at an angle of 60 degrees. It lands on a hill that is 40 meters tall. How fast is a projectile going when it hits the ground? Now again, at the very beginning, we only have kinetic energy, so we're only going to be using that 1/2 mv squared, which is here. And then at the end, we're going to have both height and kinetic energy. So we'll use mgh and 1/2 mv squared, which gives us the second part. Now, you do have an angle here, but you're actually not going to be using that angle. Because energy does not have direction, you're not going to be breaking that velocity down into components. So, the velocity that you use at the beginning will actually only be that 30 meters per second. Because the velocity that you're going to find at the end is going to be your resultant velocity, not any velocity in the y or x direction. So again, energy is a scalar. It does not have direction, so we're not even going to use that 60 degrees. So this is a very typical problem. It says a mass is attached to a spring that passes over a pulley. The other end of a string is attached to a spring with a spring constant K that is initially unstretched. Determine how far the mass will slide down the incline when released from rest in terms of m, theta, k, and g. That means our final answer will only have these variables. So it's always important to draw the mass at final conditions and identify the initial and final energies. So at the beginning, all we have is potential energy because it says that our spring is unstretched, so we don't have any potential energy of a spring. At the end, we do have our potential energy of a spring, but no height. So I want to solve for x, the distance that my block moves down the incline. So when I rearrange this, I get 2 mgh naught divided by k is equal to x squared. Now I'm going to leave it in terms of x squared for right now because something's going to happen in a little bit. Squared. Okay. Now, it said that I had to leave it in terms of m, theta, k, and g. Right now, I have an h naught there that cannot be in my final equation. So I'm going to actually replace h naught with something in terms of what I can use. Now, if I go back to my picture, I notice that x, h naught, and theta all create a right triangle. So h naught can actually be represented as x sine theta. So then I can go back over here and replace h naught with x sine theta is equal to x squared. And so then I notice one of my x's will cancel out. So it's a good thing we didn't square root earlier. And then our final equation will just be 2 mg sine theta over k is equal to x, the distance moved down the ramp. It says the mass m starts from rest at the top of a smooth, frictionless quarter circle of radius r. The upper horizontal surface is a distance 2r above the lower horizontal surface. Answer all parts in terms of m, r, and g. This really is two separate problems, so you want to make sure that you do them one at a time. The first part asks us to determine the speed of the mass when it reaches the bottom of the quarter circle. Well, even though it's curving, at the beginning it had gravitational potential energy, and at the end it's only going to have kinetic. So we can write our equation mgh naught is equal to 1/2 mv squared. Again, if we weren't given mass, it doesn't really matter because they cancel out in this case. And then our final equation will be 2g h naught square root is equal to v. But we can't leave h naught in our final equation, so we're actually going to go ahead and replace that with our height in terms of r. In this case, it's just r. The second part of the problem asks us to determine the horizontal distance delta x traveled by the blocks before striking the ground. Now, we can't use energy equations because we can't get that kind of detail out of energy equations. So we have to actually go back to using horizontal projectiles. Now, if I want to solve for delta x, I need to know my velocity in the x direction times time. Well, I solved for my velocity in the x direction in the previous problem. It was the square root of 2gr. But what I don't have is time. So remember that I can go back to the y direction, which is delta y is equal to v naught t plus 1/2 gt squared to solve for time. Now, my velocity in the y direction is equal to 0, so it just reduces down to delta y is equal to 1/2 gt squared. And again, I want to solve for time, so this rearranges to 2 delta y over g square root is equal to t. Now again, I can go back over here. Actually, before I substitute it into my final equation, I need to make a couple of substitutions. Remember that my problem said I can only leave my answer in terms of m, r, and g. So again, I have a delta y here that I need to get rid of. But my delta y actually just happens to be 2 times r. So that we can rewrite this as 2 times 2r over g, which cleans up to 4r over g. And I'm going to leave the 4 in for right now so I can make the substitution over here. So square root. Now remember that when I'm multiplying two square roots, I can actually put everything that's below both of the square roots under the same square root. What that looks like is one giant square root. 4 times 2 is 8. G, r squared over g. And then again, I notice my g's should cancel out. And I'm left with 8r squared, or 2r times the square root of 2 as my final answer.